Just give me a second to check that we are good. Yeah. YouTube. Hello, YouTube. Hello, 1,000 viewers. Are you kidding me? Hello. Okay, good. How are you doing? So after saying hi to 1,000 viewers on YouTube, what do I have to do? Press the button? Yeah. Do you have to press it again at any time? No. Good. So, hi everybody. I hope you had coffee after lunch. We're going to present Adam today, the first implementation of Adam in planetary science. What is Adam? That's the first question we should ask. Adam is a tool that stands for Advanced Geospatial Data Manipulation Platform. So Adam is the tool that will make and makes happy every day data producers, developers, scientists, and engineers. Why am I saying that? Adam goes from the backend to the front end. So you see a nice database logo in here because Adam is a database. Adam uses OGC standards to disseminate the data and to access the data. So we use CSW as an open search catalog. So you can search through different collections we have. At this moment, for planetary science, we have a small subset of the CRISM collection. We use WCS to access the data. So every time you want to retrieve data, you will run a WCS query. We use WPS to process data. You will see later on a small example. We have a Python API and a Jupyter Hub with a set of Jupyter notebooks where you can plug in, give you some space in the server to just play around with the data. And we have front end with a Mars globe where you can load images from CRISM. So small examples because I only have 5 minutes, but then we have a nice and the only e-poster session in the workshop. You can do RGB combinations, for example. RGB combinations, normally the usual way of doing it is you go to PDS, you download the whole cube, and then you load it into your favorite, I hope it's not Envy, software, and then you extract the bands, and then you do the RGB combination. So you can do the same thing, but just by filling in one URL. The result is, I choose the ugliest RGB combination ever, because it's super great. But trust me, it's an RGB combination. Then you can do, have you heard about the Bibiana CRISM products, I hope. So we processed all the Bibiana products, and you can select them by saying the name of the product, and retrieve either an RGB combination of different CRISM products, or just a single band product combination. So in this case, I think it's BD 1400, if I'm not wrong, which I'm not an expert in these products. I don't really know what you can find out using this product. I just choose that one because it was the first one in the list. So another thing you can do that, let's say in the normal way of working with this kind of data is really hard to achieve, is the special mosaics. So you can subset by just setting a bounding box, lat, long, minimum, maximum, and you will get back the mosaic of this particular area. In this case, it's a crater which is covered with some ice. There, I choose another very ugly but useful RGB combination that enhances the ice concentrations. Have you heard about WPS? Not many people. WPS, it's a OGC standard that allows you to process data using, in this case, Python routines. So you send a query-like, let's say, call, and then you get back some products. In this case, we have 5 working WPS services. The single bands that I showed you before, that you can do it either using WPS or using WCS. The RGB combination, same thing. Then band math. Sometimes some products you may think that don't really fit into your needs. So you have your equation. You can put the equation just by using B as band and then the number of the band and then any mathematical expression you want to add. And then we process that in real time, and we spit out 1 GOT for an image, basically. And then we have the queen of all this set of WPS, which is, this is the RGB combination, basically, and then the ice classifier. So before we had, Chiara was showing some scikit-learn classifiers, right? So this is running a non-supervised scikit-learn routine that basically feeds 1 CRISM image, and it gives you back 3 files. One, it's a combine of the original image plus a mask. The other one is a mask with ice, no ice, and no data. And the spectra, okay? It works really good when there is only 1 kind of ice, either H2O or CO2 ice. It works at 90-ish%, that for unsupervised, it's a super high accuracy number when there's combined H2O and CO2 ice. And then it gives 0 when there's no ice whatsoever. So this, you can also call it just by saying, I want a WPS service called ice classifier with this image. And in 2-3 minutes, you will get the image and the files and the graph. Basically, that's it, because I only had 5 minutes. So we just land on Mars for the first time. Adam landed on Mars today, and I hope you will use it from now on. Thank you. And we have the e-poster session later. You can come ask, and we will show you some things live. Questions?
What kind of ratio are you using to detect passes?
I don't remember it by heart. I can just take a look later on.
The one from the presentation. You are using the one from the presentation.
Maybe. That's my answer now. In 5 minutes, I will answer you for sure, because I will check which one I used.
So the rest of the output could be found also by remote. So you can ideally link this system with tools.
You mean by querying from external tools? I think you mean like what is
Okay. Which of the products? I mean,
the final product, the image. This is,
so for example, the ice classifier, or so feeding Adam with a different source?
No, using the source of Adam, and then port the other results to external tools.
I think that shouldn't be a problem. Yeah. As far as it's OGC compliant, happy days. Nico?
You are probably interested because I understood you had 3 different results on this module.
Yeah.
So one is the image with mask,
Mm-hmm.
which is the outcome of the classification. The second one now the spectra.
It's this one. This is the combination. So I overlay the original image with the mask, basically. It's a combination of, I don't have the pointer, but that one there, plus the original image, the original cube, combined, the result is the one on the top left.
And is there any way to include the predefined processing module use it this way? I want to call a specific routine doing
Yeah.
completely different.
As far as, yeah, we call it Python code. So if it's Python, it makes things way easier for us. Because basically WPS, we use the Python extension for WPS. So this can be plugged into Adam, and then you can call this processes routine, your code, through Adam. So basically you can take the advantage of OGC standards, basically. So calling the data using WCS instead of having to upload the data or download the data in local, so you don't actually have the data. That's it.
The compilation is made on the server.
Yeah.
Have you checked the results of the other data sets? If there is really ice?
Yeah. So with other data sets, what do you mean? With other, like MQ? Sorry.
Oh, sure. are you about the ice presence in this?
Mhm. Yeah, I mean, this module here was part of my PhD, is part of my PhD. So it is a double check. So we checked manually that this is ice actually. Yeah, you have of course you have some false positives. So you have 8% of false positives, but they are really easy to spot because the latitude and longitude are very equatorial. So you just need to take a look at the location of the image.
Further questions on the next one?
Cool, thank you.
I'm sorry. Then
Allora, PDF. Très bien. Is that the first one? Oui, c'est juste. So this is just my poster, which is behind here. So it's about the geology of Valles Marineris. I'm not sure that everyone is an expert in the geology of Valles Marineris in this room. And there are a number of new observations which are reported, so I decided not to present so many things, just nice pictures, and so that everybody can understand. So it's structural mapping of tectonics in Valles Marineris with a number of new observations which are important to understand better the evolution of the region. And since it's a big region, it's 2,000 kilometers long, it's attached to Tharsis, so it has, of course, some large-scale implications. So very shortly, we think that in general, Valles Marineris opens north-south, perpendicular to the graben that we can see here running east-west. And so I will show you a number of unusual images of Valles Marineris. Here we are in the middle of Ophir Chasma, one of these main depressions. And you can see here quite complicated features here. And this is a high-rise image. And if you are zooming to the full resolution, you will see that it's volcanic dikes. Dikes, for those who do not know what it is, it's just vertical magma sheets which are intruding the crust, like this one that you have on the right. Here we have on the right something very small, it's 1 meter wide. Here we have tens of meters wide, which means a lot of erosion because dikes have this shape, so it's going narrower and narrower toward the top and thicker toward depth. So we are looking at a deep part of the crust here. And dikes are more or less indicators of extension direction. So this is why I put these arrows here, red, which are consistent with just stretching of Valles Marineris perpendicular to the trough. So what is interesting here is also in Ophir Chasma, again, if you are zooming a lot on this, you will find extremely complicated structures, tectonic structures. And here, if you are analyzing this, you find the same direction of extension, but you are doing this by shearing the crust like this, shearing and extending, not just stretching like this north-south, but shearing in addition to this. And one of the best examples one can find for this is the shear zones that you can see in the Precambrian regions of Australia, for instance, this Gawler crater. So this is this northeast southwest. It's more or less the same direction on both features. The main shears are in the direction of east southwest here. Now something a little bit different is on this in Condor Chasma in the middle trough, and here you see that the direction of extension is now almost perpendicular. And what you can see here is in the northeast southwest direction other dikes, and this is extremely frequent in Condor Chasma. And actually, it goes even further when you are going to our Ganges Chasma for several hundreds of kilometers, you still have this continuation of direction, which show that Valles Marineris didn't just open like this, didn't shear only like this, but also open perpendicular to these directions. So it's a polyphase evolution. Not far from this, there are some very unusual observations here on the right. Again, it's always a high-res image, so you can zoom to 50 centimeters or 25 centimeters. And this typically looks like plutons, granitic intrusions in the crust. And you see also some sharp side of the rock around it. So it looks like, for instance, I found this morning this picture here of part of the Pilbara crater, which is a little bit the same type of things, where you have intrusions and some sharp contacts here and there, which are associated to the intrusion, and show that after emplacement, it was deformed by some brittle deformation. And the last thing I wanted to show you is the type of material which is affected by this type of deformation. It's a very bright material here, which is located, for those who know, below the layered deposits of Valles Marineris, that you can see actually on top here, on the top right of the picture on the left. So it is below this layered deposit. Here you have a cliff of 100 meters, again a high-res image, which shows that it's a massive, very light tone rock, which is intensely fractured. You can see all these fractures going up the slope over 100 meters. And from time to time, it has a facies of breccia, which could be impact breccia. It could be pseudotachylite, we call this like this. The same type of pseudotachylite is observed in shear zone when we have intensely deformed areas instead of impact craters. So here it's not clear exactly what it is, but it's also something which is not uncommon. And again, it's at the bottom of Valles Marineris on the floor. What kind of rock it is that we are working on this? Jonah had a talk yesterday about this with some preliminary results, but it's not yet clear because it's some kind of white basement, but it doesn't correspond to any granite, for instance. No, unfinished is the last one. No marble, nothing like this. It looks like more some kind of mafic rock, but mafic rocks are dark. This is white. So there is a problem with this. But for instance, if you look at this picture on the lower right, this is Possession Island. It's a volcano. It's completely basaltic here in the southern territories of France. And you see that alteration is systematically white like this. So it's not really an issue that we have altered rocks, which are basic rock, which are limestone like this. So, and that's all. And of course, if you have more questions, don't hesitate to ask me and look at the poster here for the implications. Thank you.
Yes. Yeah.
Pour la vidéo, elle est en bas. Ouais, alors la vidéo, tu veux juste en bas. En bas, et je clique de. D'accord, ok. D'accord. C'est un problème. Sinon, je crie. Ouais, tu cries.
Okay, I'm Pierre Fernique from the CDS, so Centre de Données Astronomiques de Strasbourg, and I will talk in 5 minutes about Aladin and HiPS planetary maps. So the title of this workshop is Planetary Maps and VO Protocol, VO Virtual Observatory, and I will speak firstly about VO Observatory, because Aladeen is a tool of the VO. It has been built started in 1999 by the Centre de Données. It is highly used presently by professional, amateurs, and other public. So we have some figures. So it's about 7,000 unique client visitors per day and 600,000 queries per day. And he implemented two important support for standards: is FITS for images, classical images in astronomy, and HiPS. It's a hierarchical system to display background of the sky, and you will see in a few seconds how we have tried to adapt these techniques to the solar bodies and to the planets. So we can see in the first approach that Aladeen is a guest tool dedicated for the astronomy, and there are two derivations of this tool. One is the desktop, and other is a light widget that you can load in your web browser. So 3 years ago, we participate to the VESPA project. So we have to start to adapt Aladeen, or to try to adapt Aladeen, because Aladeen already supports a lot of VO protocols, so TAP, HiPS, FIPS, or whatever. And maybe it could be a good idea to see how we can use it to display planet maps. Because HiPS, as I said, is for the sky, but it is a tessellation of the sphere, and mostly the planet is spheric. And we tried it, and in fact it works quite well. And it is my presentation, so here just a snapshot before the video. So a few words about HiPS. So HiPS is a AVOS standard since 2 years. It is based on helpix tessellation, so it means that you split your sphere in 12 realms, and you can subdivide these realms to reach the resolution that you need to manipulate your pixel of your surface. It is based on equal area formulae. And the best resolution of the current libraries that we have in LPX is 400 micro arcseconds. So it's quite small. For HiPS, we have no database. So on the server side, it is just regular files on a file system. And presently, for celestial surveys, we have 20 collaborative HiPS servers over the world. So we have NASA, Canadian, Japan, etc., which share the tiles of these surveys. And it represents 600 HiPS. So you have all the big missions that you know for the astronomy. So you have DSS survey, Planck, the future big missions. But as I said, we have tried to extend, and we have generated 60 planets HiPS just to play with. And at the end, it represents about 300 terabytes of data for these amounts of pixels. So, as I said, Arlene is dedicated for the celestial data, but in fact, it is more or less the same kind of tools that you need for a part of tools that you need for manipulate information over a background. So manipulate catalogs over a background, graphical tags, time series, or this kind of things. So Aladeen do that very well. So you will see that you can use it for the planetary maps. And also we have a few tools. Typically, the mock is the way to describe region, to manipulate region, to compute some operation, unions, intersection in a few milliseconds to say, okay, this data is inside this coverage, this kind of things. And also in Aladeen, you can do some calibration process for positioning your image if it is wrongly positions. So some example here. So when we start this test, we have to do a few adaptation of Aladeen. So very small adaptation. In fact, we have just to take care of the longitude display, a few syntax adaptation, and we have started to implement a few extensions of the VO protocols. So typically, EPN core has been implemented in Aladeen to load correctly the data provided thanks to these protocols. And also, so on the HiPS part of the test, the process to generate the HiPS from the original images. So generally, you have PDS images or Cartesian maps in TIFF or JPEG. So we have a tool called GEM, and you can generate the heaps from your own images from any kind of images of your planets. And it has been done with all maps provided by USGS and a few other centers providing big map. And now a video I will try. So the video will just show you how you can. So just good. So a few seconds displaying the way that you access to all the data available in the VO. So here you have a new, a new item in the tree displaying all the Mars planets. Here it is a Mars that you certainly know already. And you can reproject these maps in any kind of projection. So it is an 8-off or mold wave or tangential projection. So in fact, when you create your heaps after that, this process, you can display your tiles in any kind of projection. You can switch between any kind of heaps. So typically, I will switch to the TMIS resolution. And the result, the data in your tools arrive in this stats. And you can compare just by switching between the two panels, or to split the screen like this and synchronize the two views. So a classical operation in a GIS tool. But, and now, for the second part of this video, I will create my own heaps from a Cartesian map of Mars. So here I have my Mars data. And I will launch my heaps generator. So here it's just one single images covering all the Mars. It could be a collection of images, but in this case, all images should be calibrated. So you have to have a solution for the astronomical calibration. And I will launch this magic command which run and create the tiles. So it can take a few seconds, a few minutes, but typically for our survey, it takes a few days because you have 20, typically for pan-star survey, it takes 10 days because it is 20 terapixels. So, and you generate the tiles here. So the heaps, in fact, it's just regular files on your file system. You can expose through Apache servers. And I will just load these heaps in my Aladeen tools. Wait a minute, it's finishing the process. Takes a few minutes. Yeah, oh, it is. So you have the results here. I will switch to it. And you have exactly the same thing that's already computed heaps. Okay, and for the end of the video, I will just load some data. So typically, I will look for CRISM providers. So there is one supporting European core protocols. So here it is the tapped box of Aladeen. So I will provide my magic SQL IDQL sentence to load all the CRISM observation in this region. Sorry for this black artifact. And now I have all the information for all these observations. I have the field of views, and I can load the cubes attached to all this information. So here I cheat a little bit because it is not a direct VO protocol here. It is a TIFF results, not supported by Aladeen. So I have to convert these cubes in fits cubes. It's down here, and the result will arrive here. Okay, you have your cubes. I have removed the background because the background white border is not correctly described in the fit. It's okay. Fit. And now I can overlay my cubes over my heaps like this. Okay. And I can play with these cubes with all the tools provided by Aladeen. So typically I can extract a cut, spectra, and to draw. And this is the end of my demonstration, very fast for 5 minutes. You can normally load from your machine. Aladeen is free, and you have to load the beta version to have the support for planets. Thank you. Sorry.
Next one is Pieterek.
So this pilot. Analyze it.
Welcome back. I left you here yesterday with a promise that we'll come back to the small volcanic cones. So yesterday we discussed the large volcanoes. So these guys in yellow. And today we'll go to these small volcanoes, which are of course related to the large volcanoes. And this is a study of my PhD student from Poznań University, who is not here due to a knee operation. I just present this on his behalf. And we have the purpose of this study is to show that these small volcanic cones are related to large volcanic cones, which is the case in most Earth volcanic systems, of course. And for this, we use three indicators, let's say. We look at spatial distribution, we look at surface age, and we look at orientation of volcano summit craters or central fissure veins. I will show you examples how this looks like in practice. So this is, again, the map of this Tharsis volcanoes. So these are large volcanic edifices. These are small volcanic cones. And when you see it, the distribution, it's not random. It's somehow clustered. And this is a first indication that they are probably controlled by different large volcanoes. So we distinguished so far 6 different groups, and we measured orientation of the summit elongated crater or summit fissure. And I will show you later how this summit fissure looks like, but just look at these patterns. They are usually oriented in one way within the group. So for example, this is Olympus Mons, and then all these volcanic cones in red are oriented with this orientation. And now, when we discuss orientation, so this is what we measure, this summit elongated crater or summit fissure, okay? And another thing that we did is dating. So we dated, here are some examples for Alba Mons, for Tharsis Montes, and for Olympus Mons. And here is the summary of our results, and you can see that the age of small cones is usually quite similar to the age of large cones. So this is an example for young volcano, Olympus Mons. This is an example for an old volcano, Uranus Mons. I said it's similar, but very often is slightly younger also. And I will have also an explanation for that. So to summarize, this is how this can look like. So So these parasitic cones are associated with large volcanoes. This means they come from the same magmatic system. And we also know, based on our dating, that they are sometimes very recent. It's in terms of Martian history, 60 million years is very little. It's the latest Amazonian. Now, they are connected mostly, probably by radial dikes. The geometry has suggested us this solution in most cases. And finally, I mentioned that they are very often slightly younger than the last activity at the summit calderas. We think this might be related to magmatic pressure, which is upon decreasing of pressure, you don't have enough pressure for summit eruption anymore, but you still can produce some parasitic cones which are located lower. So this is the kind of summary, and I invite you to our poster over there. So thanks a lot, and I will take questions. Okay. So use it, please. Okay.
Next one is Alessandro.
Thank you.
So you will have that at the bottom. Maybe I can put it full screen.
Okay, so this is just to start a discussion for those of you who are mapping, are producing geologic maps with within a digital environment. I mean, commonly we are using GIS, but also it can possible to use some other software maybe. So for those of you who are not into geologic mapping, basically the geologic mapping is an interpretative process. It means that we are not doing a kind of analytical process on data. So it's not applying an algorithm, it's applying some interpretation to that. So in the interaction with the data from the user is interpretative. What does it mean? Basically, every kind of geologic mapping is based on the base map. So we do have usually imagery and DTM, hopefully, which is basically describing the morphology. So on top of this data, this imagery and morphology, we are doing interpretation. So we are using symbologies to describe which are, in our opinion, in our background, the type of terrains. In this case, it's kind of geomorphology interpretation. So we describe sediments, we describe structures, the axis of the structures, we describe what we see as limits of different possible formations, so blocks of rocks, of units. So this process ends up in this interpretative map. So this kind of process is kind of normal for a geologist which study this interpretative mapping, this geologic mapping during his studies, but it's not so common for people using to do like applying algorithms to imagery. So this interpretative mapping in the digital domain needs some really specific tools. So in planetary geology, we are dealing a lot with data, because on Earth science, usually we go on the field and we map on the field from the topography, we take pictures. And with planetary geology, we are using remote sensing data mainly. And since nowadays we are doing everything, hopefully in the digital domain, we need some elements. So we need the special registration of dataset, which is important. We need this information stacking. What does it mean? It means that we want to select which kind of information is useful, for example, or the imagery or the morphology, or if it's available, maybe a compositional map, which is co-registered. So we saw, for example, in Aladeen, it's possible to select the different layer. In QGIS, it's the same. And then another element, which is very important, is the data interactivity, which means that we should be able to load the raw data, or well, the processed data in their format in our environment. So this ends up that these geographic information systems offer a useful environment for that. Useful means that it's useful for the geologist, but those software are not being designed for geology, because the ideal geologic software means starting from drawing and then correlating every unit in a three-dimensional space and a stratigraphic order, which is not offered in the GIS system usually, because the GIS is very generic for kind of environmental analysis. But anyway, it is possible. Now all the geologic maps are made in GIS and distributed in this format because it's very practical. And so the craft of the geologic maps in a GIS needs three elements. The data interoperability, which is something we have nowadays, but 10 years ago, it's finished. Okay. The data interoperability means that we can load the maps we found on the net. Some kind of digitizing environment, it means human-computer interaction is important, because we should be using our hand to draw with a kind of smart interface instead of clicking a point on the screen. And also the symbology is important, as we see this morning. So the data models for designing a geologic map are mainly two. One is the Eulerian model, which is something that unfortunately disappeared, because it's basically, it is very similar on how we draw on the map, on the paper, and we don't need to produce layers to describe the same geologic environment. For those of you interested about that, we can speak later on the poster. And then there is the point line polygon, which is the commonly used one, with, which basically asks you to define different layers to describe the geologic map as point, linear features, or area. The only thing with these point, line, and areas is that every time, or well, we have to build a workflow to make this geologic map appearing and to be kind of practical in editing. And so we need a processing loop, which is necessary. Nowadays, there is a kind of toolbox for ARC, for the Esri software. And for free open source software, there are scripts here and there, but there is no official tool for doing that. So for those of you those of you interested, we can speak at the poster about pro and cons of each model. What are the software tools available? Maybe there is something around which I don't know still. And if we need to develop something, we can do a discussion about that. So thanks. Okay.
Antoine Séjourné. Bonsoir.
Oh, easy, easy. Putain, télécharge. Ah, parce que j'ai ta présentation.
Antoine. Ouais.
Ah, parce que je me disais, tiens, mais je connais pas Antoine.
Ouais, c'est moi.
Ok. Non, c'est ok. Non, c'est ok. Ça va. Ah, ok.
Okay, hello everybody. So Antoine Séjourné was not able to be here. He's very sorry about that. So he asked me to present a study that we did together a few years ago about a new mapping technique used for the study of the northern plains of Mars and all these strange morphology found in those plains related with the cryosphere in the northern hemisphere of Mars. It's a European, mostly European team with a financial support from the International Space Science Institute. We had a mini discussion on the 2 or 3 meeting at Bern City about it. So the scientific goal is to look at the stratigraphy and the geology of the Martian northern plains. And in those, that's the polar projection of planet Mars, the dichotomy here. And in those areas, there are many landforms of, most of them are of unknown origins. There are some rampart craters, some pits, polygons, scallop terrains, domes, and again, some circular fissures. And we try to understand with a special mapping technique, those landforms. So we decided to look at these fissures in Arcadia planitia, Utopia planitia, and Acidalia planitia, along quite important long rectangular swath of about 250 km wide and 3,000 km long. It's a lot of work to do there, of course. And we use some latitudinal trend of from 30 to 80 degrees in order to take the climatic effect on these landforms, on those landforms. So we use the CTX images, the IRIs images as well, and the digital elevation model from IRIs stereo, and the MOLA data. And so that's the classical map that we are usually using. It's quite long. We delineate each individual landforms. It takes a lot of time. It's very accurate, so for sure. But if we want to look at along a very large area on Mars, we decided to use the grid style mapping. And it's quite fast and efficient techniques. All the area correspond to some individual box, and that approach allow us to systematic identification of different landforms along that rectangular limits here. And we use the Cassini projections because there are some minimal distortion with that Cassini projection. And that's the techniques that we use with ArcGIS. that's the individual box of 20 kilometer size here. And each box, you can detect the frequency of occurrence of some individual landforms, like those one, gullies, channel, scallops, pits, polygon, and so on. And we can detect the presence or not in each individual box, like here, the presence, it's number 1, huge concentration, number 2, and nothing, 0. So we did it for the Utopia Planitia area, from 30 degrees to 80 degree north, and for different landforms, gullies, viscous flow fissure, mantle deposit, texture, textured surface, polygons, pits, scalloped, and so on. And you can see that the pink color here corresponds to the presence of these individual morphology, and the dark pink here corresponds to the huge concentrations of these landforms. And we can see some quite good concentration of different landforms in the same area here. For example, here between 40 to 50 degree north, you can have both polygons, pits, and scallop terrains. And so we look at these landforms in more details. Again, the map here, and that's the terrestrial overview of this kind of morphology in Siberia, in Yakutia. And the polygons correspond to the polygonal contraction due to the flow and freezing cycle. And here the pits correspond to the small pits at the junction of different polygons. And the depression, the scallop depression found on Mars, they correspond to these thermokarst lakes. On Mars, we suppose that all these landforms are produced by the sublimation of an ice-rich ground ice. And the close association of these individual landforms seems to indicate that we have on Mars, in that area, something like the Yedoma layer, like in Siberia, in Yakutia, you may have something like 30% of ice by volume in the permafrost in those Yedoma area. And the subsequent melting or sublimations of that ice-rich ground ice will produce these scallop depressions, thermokarst depression, polygons, and so on. So we use that grid mapping. It's what a quite efficient approach, very fast techniques, and we try in the near future to better understand the concentration of that ice-rich permafrost in those areas, and look at the charade data all around that area in order to better understand that permafrost, if it is quite a good analog or not. Thank you very much. If it is not clear after the break, the coffee break, we can discuss again about that.
And the next one is Alessandro Frigeri.
Okay, here we go. So I will speak about, I will present this Python interface to the MoonDB. So, well, is someone knows the MoonDB already? Okay, so basically the lunar samples are entering their 50 birthday. And since 2015, the Columbia University and the Goddard made a project to synthesize all the sample, all the measurement of the sample, so geochemical and petrological analysis on lunar sample, and they've been synthesized in this MoonDB database. So the Lamont Doherty Earth Observatory and NASA Goddard produced this online DB. So what is MoonDB? Basically, it's an interface to this big MoonDB, and it is written in Python and allows to design the queries, because it's quite complex. I mean, it's very wide, and also there are several options to make queries to that. So this Python, it uses Python 3 and interfaces to this data. It has been modeled as object-oriented, and it has an interface in a geospatial environment for future application which are geospatial. PyMoonDB will be presented officially in Geneva for the EPSC, but it's already available because it's ready, so you can already play with it, and it's on this GitLab of INAF in Italy. Just to orient yourself in this data model, basically we have the specimen, which is the rock or the soil which the astronaut took on the moon. We have the analysis and the analytes. So the analysis is the measurements, and the analytes, it's what is measurement, what has been measured. So the specimen is this one. In this case, we have this specimen. Then we have subspecimen. For every specimen, we have children. And so the coding is like an ID, and we have sub-ID for that. And this is the analysis. Also, the specimen has been taken in a place, so we have a landmark, and the landmark is coded as GeoGC. So it's possible to bring these analysis in a map. So in the software is ready, is published, and in the example directory there is example. This is one which is kind of funny, because this huge database can be explored in a really different way. This is one, for example. So if you look at the example, this example is going into the database and says, okay, dear MoonDB, tell me, it connects to the MoonDB and tell me how many kilograms have been bring down from the moon for each mission. So you see that Apollo era with Apollo 17, which was kind of geologic mission, is bringing a lot of data, and also we have lunar data, and the sum of everything is almost 400 kilograms of specimen and measurement. So geochemical and petrological data are in the MoonDB. In the example, you will find also a Jupyter notebook, so you can play with the data. In this case, we are querying the database for the missions and for the number of specimen and measurement, and you can play with that. Okay, so see you at the poster booth. Tell me if the MoonDB is something of your interest, if you would use the PyMoonDB, if you have special analysis you want to do, and of course future developments of that. Okay, thanks. The database basically contains all the geochemical and petrological analysis made on the samples or up to date, which have been input into the database, and there are like, I think, 23,000 analyses at the moment. So they are like spectroscopic analysis, isotopic analysis, soil composition like granulometry or whatever. It's very mixed. So within the documentation of the software, you see the different classes of analysis which nice. The interface is RESTful, and you can model from that. And the Python interface allows you to create filters on the data. So you can, for example, model a query from starting from the analytes. For example, tell me all the titanium oxide measurements made on the moon, or you can start from the mission. Tell me all the samples which have been sampled from Apollo 11. To make a what?
There's some job to be done. Now it's.
I'm rich. Yeah, good. Thanks, Stefan. Okay.
So bad that you have to a participant in the next. Yeah, I won't talk about it.
Okay.
One question? So let's take it.